So if we go back to this example that we just looked at, the 2,3-dibromopentane, we could ask how many different isomers are possible for this molecule. And if you think about it, either chiral center could be R or S, depending on whether that bromine is forward or back. And so we could have 2R, 3R, 2R, 3S, 2S, 3R, and 2S, 3S. So with two chiral centers, there's 4 possible isomers. What if we had 3 chiral centers? It's going to double again. We'd have 8 possible isomers, and so on from there. Now let's draw all of them and look at what would we consider to be the relationship between each of these structures. So I'm not going to go through formally the assigning of R and S in each case, but that's something that you could certainly do for practice. And in fact, would probably be a very useful thing to do for practice. So as soon as I'm finished drawing these, you may want to pause this video for a few minutes and go through and assign R and S in each structure. Alright, so what we have are our 4 different isomers. And we can see 2 different types of relationships. For example, these 2 yellow ones, we've reversed all stereocenters. So anything that was R became S, anything that was S became R. And the same thing for these 2 that I'm circling in green. Anything that was R became S, anything that was S became R. So when all stereocenters are reversed, that's when we would have non-superimposable mirror images, and these are known as enantiomers. So enantiomers are non-superimposable mirror images. And the noteworthy thing about enantiomers is essentially they're almost chemically not distinguishable. Enantiomers are only distinguishable in the way that we saw earlier, things with like their interaction with plain polarized light, as Pasteur discovered, or they're distinguishable when they're interacting with other chiral substances. But if we were trying to look at something like melting points or boiling points, then the enantiomers are identical. Even their NMR or IR spectra are identical. But now, what if we compare one of the green circled compounds to one of the yellow ones? Let's look at the 2 right on the top row. What we find in that case is that we've reversed one stereocenter, this one, but the other one has stayed the same. So this would refer to a situation where one of, some number more than one. So let's state that in a different way. Some, but not all, stereocenters. And stereocenters is just another word for chiral centers, carbons that have 4 different substituents. Some, but not all stereocenters are reversed. These are known as diastereomers. Diastereomers are stereoisomers, but not mirror images. And the interesting thing about diastereomers is they are actually separate molecules with, in many cases, different and sometimes very different chemical and physical properties. Now, the final category we want to mention is a kind of special case. What about achiral molecules with chiral carbons in them? So if we look at this structure here, how many chiral centers does this molecule have? So hopefully you got 2 right here and right here. But let's draw its mirror image. So there's its mirror image. And what do you think, or what would you say about its mirror image? It's the same. So we have a chiral molecule. It has 2 chiral centers, but it's identical to its mirror image. And the reason for that is that the molecule has an internal plane of symmetry. And so these compounds like this are known as mesocompounds. A mesocompound has at least 2 chiral centers, has an internal plane of symmetry, and is therefore achiral. Now, we can also have sort of the opposite effect, chiral molecules that have no chiral centers. And that might seem kind of strange to us. But recall in the last chapter when we looked at Newman projections and we talked about rotation, about a bond. Well, imagine now if there was some way to stop this from rotating. And maybe you could do that by putting sufficiently, very large groups on there, and that would prevent rotation from taking place. And so in that case, you could actually, without actually having a chiral center, you could still get a chiral molecule based on rotation because the molecule can't rotate. And probably the best known example of that, or one of the best known examples, is this molecule. So this is known as BINAP. And basically it's these aromatic rings, and it's these two planes of aromatic rings. Because of how large they are, they can't actually rotate. Now I'm going to draw the structure of this so you can see better what it looks like. And it's actually because we have these two phosphorus groups with aromatic rings attached to them out here that this molecule adopts the shape it does in this three-dimensional picture you see. And so because of that, you can actually isolate this as two different conformers, as two separate enantiomers. And at least in the case of BINAP, this ended up being important enough that in a reaction that we're going to learn in the future, hydrogenation. Hydrogenation is a reaction that takes an alkene and adds hydrogen to it using a catalyst to form an alkane. But it turns out, there's no preference for one enantiomer or one side of the molecule adding the hydrogens over the other. But if you use a catalyst that's based on this BINAP, you can actually get the hydrogenation to take place to give you one specific enantiomer. All right, one final piece. I just mentioned this briefly because many of you are going to take biochemistry in the future and you'll need to know this here, are what we call Fischer projections. Fischer projections are another way for drawing molecules. This will be one of the only times that I ever use them because I don't like them. I think they're not a great way to draw molecules, but we still see them a lot in biochemistry. And so you'll learn more about using Fischer projections in biochemistry. But basically what they represent is that you've got a carbon here at the center, and then the bonds to the left and right, those groups point forward, and the ones that are at the top and bottom point back.